In this video, we are going to define what it means to be a first-order separable differential equation. We're going to do some examples of separating our differential equations, and then we're going to do a couple of examples of actually solving our separable differential equations. Here's our definition. Basically what this says is that we are working with our first derivatives, in other words first order. It is going to be equal to some function which is going to be a mix of x and y. And we're going to separate it, or they're going to be separable, if I can write that big F of x, y as a product of two functions, f of x and g of y, where f of x is a function of x alone and g of y is a function of y alone. Let's start with some examples. I'm going to do the first two here, and then what I hope is that you go ahead and put this on pause and then try the other two on your own. My first example is dy dx minus x the square root of y. I want dy dx by itself to be of the form dy dx equals f of x times g of x. So I'm going to move the negative x square root of y to the other side of the equal sign. So I'm going to add x the square root of y to both sides. And what I end up with is dy dx is equal to x the square root of y. And there you can see that my x is a function of x alone. This is my f of x. And my square root of y is my g of y, or my function of g alone. Let's take a look at our next one here. Let's move this up. And for this one, I've got y plus the cosine of x. And unfortunately, I can't separate it. This is as good as it gets. I can't make this a product of a function of x and a product of a function of y. So here are the other two examples that I'd like you to try. So I've got y prime is equal to x squared y plus x squared minus xy minus x. So I see this and I see four terms, and I think the big F word. You're right, factoring is what I'm thinking. So on the first two terms, I see that there's an x common in both of them, so I'm going to go ahead and factor out, an x squared. So I'm going to factor out an x squared. This leaves me with y plus 1. On the next two terms here, I see that an x is common, and in particular, because of this negative between the second and third terms, I'm going to factor out a negative x. So I factor out a negative x, and I have y plus 1 as well. So that means that I have a y plus 1 in both of these two terms. See how I went from 4 terms to 2 terms? I'm going to go ahead and factor out that y plus 1 out, so I get y plus 1, and I'm left with x squared minus x. And now we can see that here's my function of x, my f of x, and here is my function of y, or g of y. On this example, I'm going to go ahead and move the x squared to the other side of the equal sign, so I'm going to add x squared, let me do that in red, it shows up a little better. So I'm going to add x squared to both sides. And I'm going to be left with y prime plus y prime is equal to x squared. Now recall from Calculus 1 that dy dx I can replace with an equivalent notation, which is y prime. So now what I do is I'm going to factor out here the y prime. So I factor out a y prime, and I'm left with y plus 1 is equal to x squared. Now I can go ahead and move that y plus 1 to the other side by dividing both sides by y plus 1, or in other words, multiplying by y plus 1 over y plus 1, but I'm going to leave it there for now because it'll help us go into our next step. On my last example, I left the y plus 1 on the left-hand side. And the reason I want to do that is because on the next step, what we want to do is we want to isolate our f of x. So what we'd want to do is get the g of y on the other side of the equal sign, in other words, the side with the dy dx. This allows us to integrate with respect to x on both sides. And you can see here that my dx's do cancel themselves out. So I'm really doing the left-hand side with respect to y. And then you think, wait a minute, I can integrate. I get my antiderivative of g on the left, I get my antiderivative of f on the right. How come I don't have c on both sides? Well, because c is a constant, I can take the c on the left-hand side and add or subtract it to the constant on the right-hand side, and it's still a constant. So let's leave the constant on the right-hand side. And the reason that we do that is because we are trying to solve for y explicitly if we can. So this is the math behind why, later in this video, I move the dx to the right-hand side, integrate, and put a plus c only on the right-hand side. Here's some things that you need to be aware of as you move forward solving your first-order differential equations. Well, first of all, not all of them are separable. Second of all, when you do separate and integrate, you may not be able to solve for y explicitly. It may be implicitly. And lastly, the integrations may not always be carried out in terms of elementary functions. And I'll do an example of that in a different video. And lastly, sometimes we'll have differential equations that have a singular solution. And what that is a solution that can't be obtained from our general solution using our usual methods of solving differential equations. So let's take a look at our first example. Let's move this up and over a bit so that we have plenty of room to work. All right, so here you can see I'm using y prime, but I'm going to move this back, or change this back to dy dx. So dy dx is equal to x the square root of y. Now, we know that we need to get y to the other side, we need to get to the left side of the equal sign, and we need the dx to the right side of the equal sign. So let's go ahead and multiply both sides by 1 over the square root of y, and that will cancel out the square root of y on the right-hand side. And let's multiply dx to both sides, and that will eliminate the dx on the left-hand side. So what I now have is 1 over the square root of y, and I'm going to write that as y raised to the negative 1/2 dy is equal to x dx. Now we're going to integrate the left and the right. On the left-hand side, I'm going to get y. I'm going to add 1 to the negative 1/2, and I get a positive 1/2. And then I need to divide by that 1/2. So I'm going to take the y raised to the 1/2 and divide by 1/2. That ends up doing a multiplication by 2. On the right-hand side, I have x to the 1. I'm going to add 1 to that, so x to the 2, in other words, x squared. And then I'm going to divide by that 2, that exponent, and we get x squared over 2 plus c. I'm going to call it c sub 1. Since we want to solve for y explicitly if we can, I'm going to go ahead and divide everything by 2. So I divide every term by 2, or in other words, multiply by 1/2. And I get y to the 1/2 is equal to x squared over 4 plus c sub 1 over 2. So if we let big C, which is just a constant, equal c sub 1 divided by 2, then we have y to the 1/2 is equal to x squared over 4 plus c. And we're getting closer. Now remember, we want to solve for y. So y is raised to the 1/2 right now. It's not solved for y yet. All we have to do now is we need to square both sides. So I'm going to square this side, and I'm going to square this side. This allows me to solve for y explicitly. So y is equal to x squared over 4 plus c squared. This gives me a family of functions that satisfied our first-order differential equation, which was y prime is equal to x the square root of y. Now, if we started out with y is equal to 0, then y prime is equal to 0. And that satisfies our first-order differential equation that we started out with. So we have a singular solution because there's no value of c that we can put in here that'll give us y is equal to 0. So we have our singular solution, y is equal to 0, and then we have these family of functions that are also a solution. This is the example where we did the big F on it, factoring. You know I was thinking factoring. I know you were thinking factoring. So we need to move the y plus 1 to the left. We need to write y prime as dy dx. And so what I'm going to do is I'm going to multiply both sides by 1 over y plus 1 dy is equal to x squared minus x dx. Let's go ahead and integrate both sides. And on the left-hand side, recall from Calculus 1, this becomes the natural log of the absolute value of y plus 1 is equal to, and then on the right-hand side, I'm going to get x to the 3rd divided by 3 minus x squared divided by 2 plus c. Let's call this c sub 1. We know from pre-calculus that exponentials are the inverses of logarithmic functions, so let's rewrite this as e raised to the natural log of the absolute value of y plus 1, and e raised to the x to the 3rd over 3 minus x squared over 2 plus c sub 1. We also know from our pre-calculus 1 rules of logs and exponents that the left-hand side just becomes the absolute value of y plus 1. On the right-hand side, we have e raised to the x to the 3rd over 3 minus x squared over 2. Now, we also know from our algebra that if our bases are the same, then we're adding exponents. So really what's happening right here is that this really is e raised to the c plus 1 multiplied by all of this lovely right here. So let's write that as times e to the c sub 1. Let's move this up a little bit more so we have some more room. Let's rewrite this as the absolute value of y plus 1 is equal to e to the c sub 1 multiplied by e raised to the x to the 3rd divided by 3 minus x squared divided by 2. Let's take a moment and talk a little bit about absolute values. So if I have the absolute value of some number a, we know that this is going to equal to a if a is greater than or equal to 0, and it's going to equal to negative a if a is less than 0. So what that means is that we can take the absolute value off the left-hand side, provided, of course, we put a plus or minus there in front of that e raised to the c sub 1. So then this becomes y plus 1 is equal to plus or minus e to the c sub 1 times e raised to the x to the 3rd divided by 3, see my 3, a little bit better there, minus x squared divided by 2. Let's move this up so I have some more space. Now, if I let big C equal to plus or minus e raised to the c sub 1, because e is just a number, 2.71-ish, raised to a constant is still going to be a constant. So a plus or minus a constant is just a constant. That allows me to rewrite this as y plus 1 is equal to some constant e raised to the x to the 3rd divided by 3 minus x squared divided by 2. Lastly, I'm going to move 1 to the other side of the equal sign, so I've got y is equal to c e raised to the x to the 3 divided by 3 minus x squared divided by 2 minus 1. And this is our general solution to our differential equation that we started out with. You should verify that there is no singular solutions on this one. Thank you for watching this video, and as we say in my class, thank you for being a part of this delicious math.